All right, so in this video, we're going to talk about the test statistics as part of hypothesis testing. We're going to talk about, test statistics. We're going to talk about statistically significant level, critical region, or known as rejection region, or critical value. So there's a lot of concept. This video can be very overwhelming and very confusing as well. So I'll try my best to go over slow and make it clear. So as part of hypothesis testing, we start with the claim, and then we assume that suppose the claim is this value here. We sample data. We collect data, and then we compute. Let's say suppose it's average, so we compute the sample mean. And then from that sample means, we want to see how far that sample means from the claim value. Is it far to the right, far to the left? Is it significantly far, right? How many standard deviation is it above the actual claim value or not? So that's what the test statistics is. It is a value used in making a decision about the null hypothesis, okay? It is found by converting the sample statistics, meaning X bar or P hat, to a Z-score, or T-score if we're looking at T-distribution, with the assumption that the null hypothesis is true. So the test statistics always follow the null hypothesis. We assume that this is the claim value. Let's look at sample data, and let's convert that sample data to a Z-score. How far is it? Is it 3 standard deviation? Is it significantly far? Is that strong enough for us to reject what we assume is true? That's what the test statistics is. Is found by, so the test, some book will denote this as Z star. It's just a Z score by taking the sample data minus the claim value mu divided by the standard deviation. And that would tell us, let me erase this here. That would tell us, how far is our sample data. Okay, so usually some book would denote different notation. I find that a little more confusing as well. So when we get to the actual example, I'll say it over again, and I'll tell you guys, what notation we use, or we're just gonna go straight with just test statistics. Okay. I have a few things here. Say that in example 3, the null hypothesis is mu equal to 3. The mean hours television that children watch per day is 3. Okay. So in example 3, that's what we have the null hypothesis. Okay. It means the mean hours television watched by children is 3 hours per day. So this is saying that what kind of data would convince the audience that the mean hour of television that children watch per day is greater than 3 hours. Now suppose that mother in Louisiana, again, we're now in collect data, okay? What kind of results she gonna get to convince her audience or convince us that the mean hours television watched by children is way more than 3 hours? What kind of sample data? Well, we would expect, okay? We would expect to see an X bar that is much greater than 3. Maybe she come back with a sample data with X bar being 5 hours. Or an X bar being 7 hours. Or maybe an X bar just 4.5 hours. Okay, which one of these we're more likely to convince? Maybe the 5 or the 7. But again, this is all subjective. I mean, if it's greater than 3 hours, but is it significant enough for us to really be convinced, right? So everything is a little bit of subjective. So that's why we have a formal procedure where we lay out everything and we capture that borderline, that critical value, that separate between data values that is significant and non-significant value, and say, okay, yes, if it's 5 hours, if it's 7 hours, it's past this critical value. So that way we will reject this, so we will support this. So, we're trying to make it more objective by assign a value. Where would that cutoff be? Okay, is the 4.5 hours greater than 3 is enough, or it has to be 5? Is it has a 7? So all that is going to come down here. All this extra thing we're going to talk about here. All right. Next thing. Suppose if the null hypothesis was true. Okay. If the claim was true, or if the null hypothesis is true that the mean hours is indeed 3 hours a day that children watch TV, what would be expected? The mean hour television that chill and watch per day from a sample data, well, we expect that the sample data will become close to 3 hours a day if it was true, or if it was just, indeed correct. So we say that we would expect the sample mean X bar to be close to 3 hours. But again, how close? Is 3.5 close? Is that close? Or maybe 4? How close? Or does it have to be on the dot of 3, right? How close? So again, very, very subjective. So to make it formal, we're going to make it less subjective and more objective. We're going to assign value, mathematical value, so that way it's clear, and there's no subjective conclusion there. So it said to answer those questions, we're going to recall the concept of statistical, I spelled this wrong here, statistical significant. So this is the concept that we study, way early on in the semester in chapter 1, I believe. Okay. So here it is. Here's some more definition for this lesson. So bear with me this one here. There's several different definitions here. So we're gonna go ahead and just read the first one here. This saying that a sample statistics, a sampled X bar or P hat, one of those, is said to be statistically significant if it is far enough away from the presumed value. Okay, what does that mean? Of the population parameter to conclude that it would be unlikely for the sample statistics to occur by chance if the null hypothesis is true. So this definition, we're going to extract this and we're going to start assigning values to make sure that it's concrete. So far away, okay, so we're going to say, what does it mean by far away? What does it mean by unlikely? What does it mean by occur by chance? So by standard, before this chapter, that means the cutoff point is 5%, if you recall that. So now in this chapter, we can control, it doesn't have to be 5%. We can control that value. Where will be the cutoff point? What does it mean to far enough away from the presumed value? We have that ability to control that cutoff value. Okay, and that cutoff value is what we know already, is alpha. Okay, that is the probability, that is the significant level, that saying that, okay, well, this is what we use to determine whether a data value is constitute a significant evidence against the null, or by nature, the significant level alpha is the probability of mistakenly reject the null hypothesis when it is indeed true. So all that is a lot. To sum this up, we go back to this example here. Now, suppose the mother of Louisiana went out and sampled 20 children and come back with, a sample means of 5 hours. Okay. Well, if the assumed value is 3, 5 hours is 2 hours above the 3. Well, divide that by the standard deviation, how far that is. Okay. So that's what the significant level is. We allow us to set that boundary or that critical value. So in case we reject the null, we have this much chance of making that mistake. So the significant level, this is saying that it is the probability of mistakenly reject the null hypothesis when it's true, or right now at this point, we're just going to go with the first sentence here. Just saying that it is the probability value that used as a cutoff for determining when a sample data is significant versus not significant. So very similar to the range rule theorem that we discussed early on in the semester, and that just to show some data values and usual, not usual. Now we look at probability and much more complicated concept. The next definition we have is critical region. This is the area corresponding to all value test statistics that are statistically significant, which cause us to reject the null. Critical values. So we kind of briefly mentioned this throughout the semester already. So those are the values that separate the critical region from the values of the test that is not statistically significant. All this is a lot. Okay, so hopefully when I draw this picture, it makes a little bit sense. So in terms of picture, okay, suppose we are trying to do a test on a claim regarding the population mean. Then we look at the distribution of X bar, certain size, n. Okay, so let's say this is the distribution of sample means of the number of hours of television children watch per day, for example, right? If this is the distribution of x bar, from the central limit theorem, we know that the mean of all sample means is equal to the actual mean itself. So we have that. Central limit theorem say that mu of all x bar is equal to mu, sigma of all x bar equal to sigma over square root of n. Okay, so the critical region, suppose we have these here, we have these regions, so this is where we do the cutoff. So this would be the critical values. Okay, all right, critical values. So if you recall, this is where we separate the significant region from the non-significant region. So non-significant region, or significant value, if you remember, right? So we define these non-significant region as a non-rejection, and we define the significant region will be the rejection region. And we'll discuss what that mean by rejection and not rejections. So this be the non-rejection. Okay. So the significant level is alpha. Okay, so this area here is alpha. So that's alpha. Okay. So before this chapter, we look at the range rule of thumb, 2 standard deviation above the mean is, considered to be all the user data, and anything past 2 is a, significant high or significant low. And this here, we're gonna use the same concept but apply to probability, and that's what we do in this chapter here. Okay. So what's going on here? Suppose we assume mu equals some value. We look at a sample mean. Let's say this is sample mean. Okay, so that's just from sample mean with certain size n, and then we say, okay, well, is this distance here, is that okay? Is that close enough to mu, or is it too far away from us to say, okay, mu equal 3 is not true, right? So in this case here, x here is in the non-rejection region. So in this case, that even though it's not equal to the value mean, it's still considered to be, somewhat relatively close to mu. So we won't reject or claim we won't reject our null hypothesis. If x bar was to be over here, then, this say we reject the null. Okay. All right. So all this right here, we can summarize this using some numbers and really make sense of, is 5 hours enough far away from 3, or it has to be 7, or down here is 3.5, is that the cutoff value, is that close enough, or it has to be 4? So when we do an example, it makes a lot more sense what this means. So right now, all it is just a bunch of notation, a bunch of definition, and it can be very confusing. But, I'll let you guys process through this, and again, we can talk more about this on Zoom. So I expect that this section of this chapter here is going to be a lot more confusing than the previous one. So